Audio Jungle. Audio Jungle.
Hello everyone, myself Narendra Singh Maurya. So guys, today we'll solve GATE 2015 jet propulsion problem. All right, and here we have problem number 11. All right. So the problem is which one of the following aero engine has the highest propulsion efficiency? Okay. So this question is what? For the propulsion efficiency option they have given turbojet engine without afterburner, turbojet engine with afterburner, turbofan engine, ramjet engine. Okay. So we should know like what is the propulsion efficiency. Okay, propulsion efficiency. Efficiency eta p. Okay, so we know eta p generally that formula is very in short form it is 2 alpha divided by 1 plus alpha. All right, what is the alpha? It is the velocity ratio. Alpha is nothing but vi by Vj, or you can say V infinity by Vx. All right. So this is the formula. Anyway, this is the very short form. Another formula I will write here, that propulsion efficiency eta p. Okay, which is nothing but thrust power divided by thrust power plus unutilized kinetic energy in nozzle. I must write this. Okay. Okay, what is the thrust power? Thrust is power is nothing but thrust into velocity divided by again thrust into velocity plus what is the unutilized kinetic energy? That is nothing but velocity of aircraft. Okay, this is velocity of aircraft. All right, plus unutilized kinetic energy, and unutilized kinetic energy is nothing but m dot a in bracket v exit minus v infinity square. This is the formula. So you can check both places we have a thrust power. Okay, both places we have a thrust power, which is nothing but I must write thrust into velocity divided by thrust into velocity plus change in kinetic energy, and this is the loss in nozzle. So in numerator and denominator both places we have thrust power. Okay, we can write here thrust into velocity, thrust power divided by thrust into velocity plus delta ke. This is the unutilized kinetic energy, or you can say loss of kinetic energy. Okay, loss of kinetic energy in nozzle. Okay, so kinetic energy basically that propulsion efficiency will be depending on the one quantity, which is the change in kinetic energy or loss in kinetic energy in nozzle. All right, so if loss will be more, then propulsion efficiency will be less. If loss will be less, okay, then obviously this denominator will be more. I mean, you can connect this like if loss of kinetic energy in nozzle will be more, so this denominator value will be more and theta p will be less. If this loss of kinetic energy in nozzle is less, so denominator will be less, hence eta p will be more. So eta p is what basically inversely proportional to loss in kinetic energy in nozzle. Now, as per given option, turbojet engine without afterburner, turbojet engine with afterburner, turbojet engine, and ramjet. So ramjet engine, obviously loss in kinetic energy in nozzle will be more. Why? Because it is very high speed. Exit is what, supersonic, right? So if you check the formula for the loss in kinetic energy, what is the formula? I have written delta ke. So it is nothing but 1 by 2 m dot ve minus v infinity. What is ve? Exit velocity. V infinity is the aircraft speed. Okay, so ve is very high, so delta ke will be very high, and delta k is very high, it means eta p is very less. You got my point or not? Simple. So VE exit velocity, which is the hot velocity, okay, hot air. All right. So this velocity will be very high for the ramjet. So KE will be very high. So propulsive efficiency will be very less. Thermojet engine with afterburner, it is also similar condition, like very high, because afterburner you are using, it means very high exit velocity. And turbojet engine without afterburner, okay, there is no afterburner, but still it is turbojet. So all the velocity you are getting from the exhaust, which is hot gases. So again, you will have a very high loss of the kinetic energy in nozzle. But what about turbofan? Check turbofan, you will have two nozzles, cold nozzle and hot nozzle. So if you talk about the losses of kinetic energy in turbofan, so it will be very less. So and at the same, why it is less? Because exit velocity of the hot gases will be less. At the same time, cold nozzle will also have a velocity, and you will get thrust because of cold nozzle as well as hot nozzle. So I can say here, like, loss of kinetic energy in nozzle in turbofan is very less compared to all three. Okay, so in case of comparison of propulsive efficiency, so obviously turbo engine will have a very high propulsive efficiency, so your option will be C. So what is the correct answer? Option C. I hope you understood this. Okay, answer is C. All right. Okay, this is the next question. Okay, this is question number 12. The stoichiometric fuel to air ratio in an aircraft engine combustor varies with the compressor pressure ratio as follows. Okay, what is the stoichiometric ratio? Stoichiometric ratio means fuel air ratio. What is the stoichiometric fuel air ratio? So simple, see, this is the combustion chamber. This is the mass of air entering, okay, mass flow rate. This is the mass flow rate of the fuel entering, and here we have m dot a. This condition, this is what combustion chamber. Okay, so basically, what is the stoichiometric fuel air ratio? Means m dot f by m dot a. What is this stoichiometric? So stoichiometric will also be called, okay, will also be called ideal fuel air ratio, will also be called ideal. The word they have used is stoichiometric fuel to air ratio. That means that proper amount of the fuel and proper amount of the air when it is going to mix in combustion chamber, so that combustion should be proper, and that combustion should be optimum, and that is called optimization of combustion chamber also. So what should be the proper amount of fuel and what should be the proper amount of the air when you are going to mix in combustion chamber, so that it can raise the temperature as well as pressure, highest condition. Okay, so that highest, because if whatever fuel you are burning, that thermal energy you are going to convert in kinetic energy in turbine as well as in nozzle. All right. So that, so particular that reason, what should be the proper mixing of the amount of the fuel and amount of the air, that should be the highest, that should be the optimization condition. So that proper amount, that ratio of the fuel and ratio of the air, that is also called ideal. So that will not be depend on the, compressor pressure ratio. See here they have said, it is depending on the compressor pressure ratio. No, it is not going to depend on compressor pressure ratio, because it is fuel to air ratio you are going to give, that is the input. They are not talking about the after burning what is going to happen. They are saying like when you are going to take the appropriation, like what should be the amount of fuel and what should be the amount of the air, so that will not depend on the compressor pressure ratio. All right. All right. So hence, what is the correct answer? That is the independent. Will not go for increasing non-linearly, decreasing, because it is totally independent. This is the mixing of the fuel and air. That amount what you are going to use for the combustion, for the proper combustion, what are the amount you are going to take, like for the fuel and for the air. That amount, that ratio will be called as the stoichiometric ratio. That's the reason I told you this ratio also called as the ideal fuel to air ratio. All right, so that will not depend on the compressor ratio. Okay, so what is your correct answer? I must say answer is nothing but C. All right, good. Now this is the next. This is the problem number 24. The isentropic efficiency of aircraft engine operating at a typical subsonic cruise condition with the following components: intake, okay, compressor, turbine, nozzles, are denoted by eta I, eta C, eta T, eta N. All are the isentropic efficiency respectively. Which one of the following is correct? So, check. This is what gas generator. All right. Okay. This is A. This is 1. This is 2. This is 3, 4, and exit. Right. So A21 called intake. Okay. 1 to 2, it is called compressor. Okay. 2 to 3, it is called combustor or combustion chamber. Combustion chamber. Sorry. This should be anyway. I will write here. Okay. And 3 to 4, this is what turbine, and this is 4 to E, which is called nozzle. All right. Now, if you draw the TS plot, wait. Okay, this is A21, this is 01 dash, and this is 01, not quantity, total. This is not 2 dash, not 2 dash means ideal, isentropic. Huh? Check TS. This is not 3, okay, not 4, this is not 4 dash, this is the 5, or this is 5 dash, or you can say this is what? Let me check. 4 to 5. This is exit, or you can say 5. It's your choice. Okay. Now, so for all the cases, like for nozzle, okay, we have nozzle or sorry, intake or diffuser. This is what compressor. This is the combustion chamber, turbine, and this is what? Nozzle. All right. So for all the components, if I will say first intake, so intake efficiency is what? Eta I. Isentropic means you are talking about the temperature. Okay, there you are talking about the enthalpy, you are talking about the temperature. So what is the like intake will give the efficiency, which is because intake itself a diffuser, it is like a compressor because it is increasing the pressure and temperature. So you have to write isentropic temperature rise divided by actual. You can write enthalpy also, isentropic enthalpy rise or isentropic temperature rise, meaning is same, actual temperature rise. So here what is the isentropic temperature rise? I must say it is nothing but T naught 1 dash minus, you just say this is the A point, TA, okay, or you just say not A, so this is not T naught A, means total pressure, okay, total temperature, and this is nothing but actual temperature, so T naught 1 by T naught A. So what is the intake efficiency? That appropriate value for the intake or diffuser is given, that range is given, okay. I must write intake which is less than 0.9 and greater than 0.7. So actually big losses, na 70% efficiency is very less. That means losses is more, and that is true in nozzle and in intake losses will be more. Intake, at least in intake, because of the flow separation and all, and similar things happens in a nozzle also, because of the flow separation and all. There will be the losses, huge losses. So that efficiency is 0.7 to 0.9. Depends on the designing, depends on the Mach number also. Okay, but this is the range. Similarly, compressor, I must say, again eta C, isentropic temperature rise divided by actual or real actual temperature rise. Check what is the isentropic temperature rise. It is nothing but T naught 2 dash, sorry, it is nothing but T naught 2 dash minus T naught 1 divided by T naught 2 minus T naught. This is the efficiency. Yeah, T naught 2 dash minus T naught 1. All right. So this eta C also will have a range. Okay. What is the eta C? Eta C is less than 0.9 and greater than 0.85. This is the efficiency for the compression. All right. Similarly, because in the problem they have asked the intake, compressor, and then turbine, so we'll go for the turbine. So what is the turbine? In turbine always expansion occurs, so you can say isentropic, sorry, not isentropic, it is now just reverse, no? Compressor and turbine. So now there is the fall of temperature and pressure, because in turbine, you know, expansion takes place. So you write actual temperature drop divided by isentropic temperature drop. Okay. What is the actual temperature drop? Check. Actual is T naught 3 minus T naught 4 divided by T naught 3 minus T naught 4 dash. And this eta T also will have a range. Okay, this is the very fixed value I am telling you. You need to remember. This is less than 0.95, okay, and greater than 0.9, okay. Similarly, we'll go for nozzle. Eta N. What is the nozzle? Again, it is like a turbine because it is also expand the flow. So actual temperature drop divided by isentropic temperature drop, which means actual temperature drop means what? Check. T naught 4 T naught 4 minus T naught 5 divided by T naught 4 minus T naught 5 dash. If you check the nozzle, this is also, that value is nothing but it is less than 0.98 and 0.9. This is the range for the nozzle efficiency. Okay. Now, if you check the efficiency, so which one have a higher efficiency? Check among all three. 98 means 98%. That is the maximum. So nozzle will be maximum. Check which one option. Nozzle is maximum. Nozzle, all four options they have given eta and maximum. So that is the first. After nozzle, we'll check which one is the appropriate answer, because nozzle is what expanding the flow, so losses will be less, but compressor and diffuser will rise the temperature and pressure, so flow separation chances, or you can say that reverse flow chances. Okay, so losses will be more in compressor and diffuser. So obviously after nozzle, check 95% you are getting in turbine. So 95% efficiency you are getting in turbine. So this is the turbine, and this is the compressor, this is the turbine, and this is the intake. We'll check the intake also. What is the intake efficiency? Wait, it is the zero 0.9 and eta I. Okay, so efficiency is less. So now we'll go for the this value. 0.98 is nozzle, and actually that wait, because nozzle and diffuser is non-rotatory part also. Okay, so that losses of here it is let me correct this value here. I have made mistake. One thing I want to add here. Okay, this is 0.96. Okay, because this diffuser will have a like a non-rotatory part. So compressor and turbine, obviously diffuser will have a more efficiency compared to compressor and turbine. That need to be careful, because intake diffuser and nozzle will not have a rotatory part, so obviously that efficiency will be more. So now that compare this value, so we got 96. So 96 efficiency will have a obviously compressor is less, turbine is less, so 96 will go to 96 intake, which is option 2. This is the intake. Okay, now we'll go for the next. What is the third one? So we'll find that correct. Third is turbine, 95. So I must say this option C is your correct answer. What is the answer? Hope you understand. Just compare this there. Nothing we have to do, is just compare. All right, so answer is C. Done. So now you got your answer. It is nothing but C. All right. This is the next question. Sorry. Now this is problem number 39 for 2 marks. Okay. All right. So check. And air enters an aircraft engine at velocity of 180 meter per second with the flow rate of 94 kg per second. The engine combustor requires 9.2 kg per second of air to burn 1 kg per second of fuel. Okay, the velocity of gas existing from the engine, exiting from the engine. Okay, so first I will write given data. The aircraft velocity they have given v infinity. How much? 180 meter per second. Mass flow rate of air, how much? 94 kg per second. Then they have given the velocity of gas exiting, means exit velocity they have given to us. How much? It is 640 meter per second. The momentum thrust. All right. And data they have given to us, we need to careful for this. They said we have combustor. Okay, they said we have combustor, and for the combustor they have said 1 kg of fuel. Okay, m dot f, they said 1 kg per second of fuel. If you want to burn, then what amount of air you required? it is given 9.2. Okay, so 1 kg per second of the fuel, if you want to burn, then 9.2 kg per second of air you need to supply to the combustion chamber, all right. So what is the mean of it? Its meaning is simple. 1 kg per second of, if you are supplying 1 kg per second of air, okay, then it will burn 1 upon 9.2 kg per second of, okay, 1.92 kg per second of fuel it will burn. Hope you understood. 1 kg per second of fuel if you want to burn, then 9.2 kg per second of air you need to supply. If I will supply 1 kg per second of air to the combustion chamber, then it will burn only 1 by 9.2 kg per second of fuel amount. That's the mean of it. Then what will be the air you are supplying? You are supplying 94 kg per second of air you are supplying to the combustion chamber actually. So it will be 9.4 divided by, sorry, it is not 9.4, it is 94, sorry, no? It is 94. It is 94 divided by 9.2 kg per second fuel required. Okay, all right. So for 94 kg, because actually you are supplying 94 kg per second of air, so for this what amount of the fuel required? So that amount of fuel you can say will be 94 divided by 9.2. Let me calculate this. It is nothing but, okay, wait, 94 divided by 9.2, it is, I'm getting 10.21. I'm getting 10.21 kg per second. So actually for the aircraft, okay, for this aircraft, okay, okay. So here 94 kg per second of air is what supplying. So here fuel must be 10.21 kg per second of the fuel. What is the exit? Exit is nothing but how much it is given? Check. It is given 640, I think. No? 640 meter per second. All right. And the velocity of the air they have given how much? Entering 180 meter per second. All right. So now we got actual data. Actual data is 94 kg per second. M dot F we got 10.21 kg per second. V infinity we got how much? We got 180 meter per second, and V exiting velocity we got 640 meter per second. They are asking thrust, and what thrust they are asking? Check. Momentum thrust, they said. Momentum thrust in Newton. All right. So we know the thrust formula. We have thrust, and thrust is nothing but momentum. Thrust, okay, momentum thrust plus pressure thrust. So this value is what? Zero. Na? Pressure thrust they are not asking. They are asking only thrust, and that thrust is nothing but momentum thrust. What is the momentum thrust? Here we have exit velocity and mass flow rate. So what is the mass flow rate? M dot F, and this is M dot A. Simple. Yes or no? And if you check what is the exit here, exit will be M dot A plus M dot F. So what is the momentum thrust? This mass flow rate into velocity. which is nothing but exit velocity, and this is the inlet velocity. We just try to understand inlet velocity. What is the momentum? That is change in velocity into mass flow rate. So what is the mass flow rate here? It is m dot a plus m dot f into exit velocity is ve minus, here it is nothing but m dot a into vi. Yes, so finally you got thrust, which is nothing but momentum thrust. What is that? M dot a, m dot f into ve minus m dot a into v infinity. What is the m dot a, check? It is 94. What is the total amount of fuel you have injected? It is 10.21. ve, what is the exit velocity? 640 meter per second minus m dot a 94. What is the v infinity? It is 180. We'll calculate this. Okay, what is the value? Wait, 94 plus 10.21 104.21 into 640 minus m dot 94 into 180. I'll get here 49,774.4 Newton. This is what thrust. Check the option. 49774. 49774. 49774. So approximate this. Check. 49779. Here you are getting 49774.4 Newton. So because this unit is what given in Newton, so I think option D is very close to this 49779, or you can say 49. It is approximate to our answer. What is our answer? 49. Wait. Our answer, whatever we are getting, that is approximate to 49774.4. This is the answer. It's very close, no? So what is the correct answer? That answer is nothing but option D. 4977. What is the option D? 9. That is the answer. Approximate. Okay. Done. Hope you all understand this. Okay. So do hard work, like and subscribe the channel. Okay. Keep doing hard work. Thank you. Thank you all.